Hello, statisticians. Welcome back. Today we are going to be finishing up section 10.2 on comparing to means, and that's going to be the end of chapter 10 here today. So we're going to think back to the example from yesterday about the calcium and the blood pressure. Feel free to go rewatch that example or look at your notes. But basically, we can estimate the difference in the true mean decrease in blood pressure using a two-sample t interval. So yesterday we did a two-sample t test for this. We're going to do a two-sample t interval for mu1 minus mu2 to compare it to the results we got with our test. However, yesterday we did a one-tailed test at 5% or 0.05 significance level. So what we'll do is we're going to use a 90% confidence level for our interval that will leave 5% in each tail. Okay, and that will match this 5% we got for our one-tailed test. We already checked the conditions yesterday, so it's the exact same. If you use table A and a conservative estimate for degrees of freedom, you will look up a critical value of 1.83 for that 0.05 upper tail probability with 9 degrees of freedom. You could also use your calculator and use the degrees of freedom your calculator gives you, which will then give you a different critical value because it will have a different degrees of freedom. You could also have your calculator just run a confidence interval like we learned how. But if you are using the conservative number 9 and the table, you'll get the following interval. Okay. If you use your calculator, you'll get a slightly narrower interval, but it'll be reasonably close to this interval. All right. So you can see that we are 90% confident that the interval from negative 0.754 to 11.3 captures the difference in true mean blood pressure reduction on calcium over placebo. Now, often what we did with the intervals, we compared it to the null hypothesis, and our null hypothesis was 0, and you can see that 0 is in this interval. So because the 90% confidence interval includes 0 as a plausible value, we cannot reject the null hypothesis of 0 against the two-sided alternative at the alpha equals 0.1 significance level, or against the one-sided alternative at the 0.05 significance level. Okay, so you can see that that result matches with what we got yesterday in our test of failing to reject the null hypothesis because the hypothesized value is in this interval. Now, something to think about is why didn't we get a significance difference? The mean difference between the two groups was 5.273, which actually is a fairly large difference when you're measuring blood pressure. The thing is, the reason why we didn't really get significance results is because our group sizes were very small. Okay, so with small group sizes, however, this difference wasn't large enough to reject the null hypothesis in favor of the one-sided alternative. Now, we suspect that larger groups might show a similar difference in blood pressure reduction, which would indicate that calcium has a significant effect. If so, then research in this experiment made a type 2 error, that is, failing to reject a false null hypothesis. In fact, that is actually what happened. Later analysis of data from experiments with many more subjects actually got a p-value of 0.008, even though the difference observed was very similar to this one. So sample size actually strongly affects the power of a test. Remember, the power of a test is how likely it is to correctly reject a false null hypothesis. So a large sample size greatly increases the power. Basically, the idea is it's easier to detect an actual difference in the effectiveness of two treatments if both are applied to a large number of subjects. So next thing we're going to talk about is using these T procedures wisely. So the two-sample T procedures, that is intervals or tests, are more robust against non-normality than one-sample T methods actually, especially when the sizes of the two samples are equal and the two populations being compared have distributions with similar shapes. And then probabilities from the t-table are quite accurate for a broad range of distributions when the sample sizes sometimes are as small as 5 for both. Okay, so while that is true, we are not going to change our rules, though, for when to use t-procedures. Basically, we're going to still use these same rules to not complicate things. So if the sample sizes are less than 15, use two sample t-procedures if the data are close to normal. That means roughly symmetric, single peaked, and no outliers. If there's skewness or outliers, do not use t-procedures. And then we've got that middle group, if it's between 15 and 30. So at least 15, but less than 30. Well, then we're going to use t-procedures in some more cases. But still, if there's strong skewness or outliers, don't use t-procedures. However, in this case, it could be bimodal or not perfectly symmetric. You could get some other shapes here. But if there's strong skewness or outliers, don't use t-procedures. And then large samples, if it's more than 30, we can use t-procedures for things that are clearly skewed or outliers when both sample sizes or experiment groups are large, and that we're defining that as greater than or equal to 30. Some other cautions and considerations to make when using t-procedures. First, in planning a two-sample study, choose equal sample sizes if you can. So if you are ever asked to create a study or experiment, try to make the groups the same size. Next, do not use the pooled two-sample t-procedures. On your calculator, always select no. Basically, this was an option left over from time when we didn't have great technology to do statistics with. When you had to do a lot of calculations by hand, there was this procedure called pooling, which made it easier. But because of the technology we all have available to us now, there's no need to use the pooled option. So never use it. Next, we are safe using two sample t-procedures for comparing two means in a randomized experiment. So even if the data doesn't come from a random sample, we can still use these procedures for random experiment. And we saw that example in the cholesterol or the blood pressure study. Those subjects were not randomly selected, but we could still use the procedures because it was a randomized experiment. Now, let's talk a little bit more about this one. Do not use two sample t-procedures on paired data. So let's think about what that means. So here I've got two settings, okay? And I would like you to think about for each of them whether you should use paired t-procedures or two sample t-procedures, okay? So if you remember, paired t-procedures, we learned about those in Chapter 9. That's basically doing a t-test on paired data on just the differences. And now in Chapter 10, we learned two sample t-procedures. So for each of these situations, decide which of these two should be used. You can go ahead and press pause, read those over, and then press play when you're ready to check your answer. Okay, welcome back. Did you actually press pause and do it? Did you? Are you lying? Okay, I hope you did. Here we go. Here are your answers. For the first one, A, you should have chosen paired t-procedures, and we learned how to do those in Chapter 9 because, a single tire can be paired from brand B can be paired with a single tire from brand A that were on the same car. Okay. And then we compare each car's A and B and find their differences and then do a t-test or a t-interval just on the list of differences. For the second one, that would be a two-sample t-procedure because there were two different groups randomly assigned to two different treatments. No reason to compare one individual worker to another from the two groups. It does not say that each worker, experienced both treatments. So we are just comparing one group to another, and that's going to be two sample t-procedures. And then finally, last word of warning or caution about using t-procedures is beware of making inferences in the absence of randomization. You might not be able to generalize results to a larger population of inference. And if you think back to the calcium and blood pressure study from yesterday when we were talking about our conclusion, which I had in yesterday's notes, our conclusion we just made about the the people like the ones in this study. We weren't able to make them about a larger population because we weren't taking a random sample. Okay, so pay attention to whether or not it's a sample and what type of conclusion can be made. Well, that is it for 10.2, which means your homework will be due. Check the instructions on my HA about that. And that means we are now also done with Chapter 10. Way to go.